Hi, my name is Thomas Kim. In this session of video, I am going to explain how to implement rational numbers or fractions in C++, and I will explain why important. I have seen lots of programmers who cannot deal integer division properly. Integer division is really tricky. If you haven't experienced it, you are very lucky. But in my case, in my course of programming over 20 years, integer division is actually really tricky. So in this session, we will implement rational numbers and to solve the problems that we face in integer divisions. To give you a concrete example about the problem related to integer division, I will make a simple code and I will show you why integer division is so much tricky. So in combinatorics, we have like NR, or it is called NCR in some European countries, or also in Korea. We say the number of combination out of n elements, n distinct elements. We select r elements, then how many ways can we choose r elements out of n distinct elements? It is called combination. About combination, please leave it to Wikipedia or some other materials, some other YouTube, and I will explain how to implement properly, how to implement this calculation properly in this session. And in the course, we will implement rational numbers. Combination is actually basically calculated like this. Calculated like this: r factorial n minus r factorial over n factorial, and it can be, this equation can be written like this: r times r minus 1 times 2 times 1, then n times n times n minus r plus n. So if we don't implement this equation properly, we are having problems, because this is integer. Integer is divided by another big integer. These are very big integers. So I will implement this in C++ code, then I will show you why this becomes problems. So I will name this function like int maximum integer supported in C++ in Windows platform is int max. This type, this is actually long integer. This is 64-bit integer type. So I say combi NA. Of course, NA are two parameters, and I would say NR. These two parameters are of type int max t. int max t is actually defined in C std int header file. Okay, so here I will make a very simple code like this. If r greater than n minus r, for example, then I would set r n minus r like this. Then we are going to compute NCR, NR or NCR. We will compute this. We will say double RLT equals 1, for example. Then we do loop, for example, like this for int max ti equals 0, then I is less than r, then plus I, like this. Then we do RLT times equal like this. Then we say n minus I over r minus I, like this. See? You understand this? Then we return RLT. You can say INT, max T, RLT. This is typical implementation. Of course, we can have more code here, but this is actually typical implementation of combination, like this equation. This is actually something like this: r minus 1 times 2 times 1 over n minus 1 n minus r plus 1. If we present this as C++ code, we can present like this. So here we declare the double variable RLT, and we compute these terms. Then we return as integer. If we implement combination NCR or combination like this, let's try it. If we give this number n 30 and r7, then this function gives this result. Here, this result is wrong. The true value, the correct answer should be this. There is one difference. Okay. Also, if we try 30, 12 like this combination, it is like 30, 12 like this. If we compute like this is also wrong. Here 4, here 20, 225. This is correct result. So this is correct. This is wrong result. This is correct result. If we implement combination like this, we are apt to have very wrong answers like this. When n and r is less than 20, for example, 20 or equal to 20, this equation holds. Okay, right. But if it becomes like 30 and 30, then this combination doesn't hold. It is because integer is divided by another integer, and the result is assigned to double. Okay, so it causes overflow because when computer stores the real number or floating point number, it is not actually exactly correct. So we have to deal this kind of problem properly. Otherwise, this kind of bug is really hard to detect. And to explain how to fix this problem, we have to make rational numbers. This is the purpose of this video. Before we implement rational number, I will give you some background information. And I need to define some terms to explain rational number. We let rational number as R. It is composed of two numbers, n over d, where n is called numerator, and d is called denominator, where, of course, n and d are integers. Okay, we define numerator, denominator. And I also need to define G. When I write G, it means it is greatest GCD, greatest common divisor of two numbers. For example, A and B. For example, like this. GCD means greatest common divisor. When I denote L, symbol L, it is called LCM of A and B. This is called least common multiple. Let A times G, B equals B times G, where A and B are coprime, or is called relatively prime. Then GCD of A and B equals GCD AA, AG, BG, it is G. Okay, this is greatest common divisor. And LCM, L is defined like this, LCM, LCM of A and B, LCM AG, BG, then we let A, B, G. This is LCM, greatest common divisor of two numbers. So basically, you have to remember these equations, these terms and relations. And there is one more relation between these numbers. If we multiply A and B, A times B equals ABGG. A, B, G, G. We have like this. Then if we let this term ABG is L, so we have A times B equals L times G. We evaluate or compute GCD of A and B using Euclidean algorithm. Using Euclidean algorithm, we compute the G, greatest common divisor of two numbers. To compute L, least common multiple, we can compute like this. If we divide each side, if we divide G over 1 times G over 1, if we multiply both sides, then it becomes like this, and L. So if we rewrite this side, L, G, A times B. Okay? So L becomes G over A times B. When we compute L, least common multiple, we have to compute like this. G of A times B, or A times G over B. We have to compute like this. if we compute this way, we should not compute this way. I will tell you why. For example, if A is 10 digit, and B is like 12 digit, 10 digit integer and 12 digit integer, for example. If A times B gives us 21 digit, 10 times 11, 21 digit. It's a huge number, 21 digit, right? 21 digit. If A is 10 digit, B is 10 digit. It overflows. Overflow. Let's see. Biggest integer in Windows platform, 64-bit platform. The biggest integer is int max t. This is actually long data type. And this is a 64-bit integer. Its maximum number is 9, like this. And it is 18 digit correct. This is 18 digit, right? This is maximum number that can be represented using long or max int max t. This is 18 digit correct. If we multiply 10 digit and 12 digit number like this, then we have 21 digit, and this 21 digit cannot be represented here. So if we compute like this, A times B over Z, we have overflow, not like this. We have to do like this. Either A divided by Z times B, or A times B divided by Z. This term effectively gives B, this term effectively gives A, such that it becomes A is AG, for example, this term is B. So A, B, Z, correct. Okay. This in this case, this term gives A, for example, B gives BG, so A, B, Z, correct. So we have to compute like this, not like this. We have to be very careful. For any integer of the form, for example, 12 over 10, 10 over 12, we can reduce like this. 2 times 6, 2 times 5, then we have 6 over 5. This form is called reduced form. If we present it like n over d, then we can let n prime d prime like this. Then n prime would be n divided by g. D prime would be d divided by g, where g is GCD, greatest common divisor of n and d. We call this reduced form. So in reduced form, reduced form, n prime, d prime are coprime, or relatively prime. In Korean, we say coprime 서로소. Coprime or relatively prime, we say 서로소. N prime, D prime are coprime. So I defined reduced form or reduce. Now we are going to learn rational number multiplication. So suppose we have two numbers such as 35 over 6 times 33 over 10. We are multiplying two rational numbers like this. Then we can set like this: 2 times 3, 5 times 7 times 2 times 5, 3 times 11. Okay? We should not do like this. We should not do like this. 2 times 3 times 2 times 5, 5 times 7 times 3 times 11. In computer, if we do like this, we are having overflow. We cannot do like this. The better way is something like this. The proper way would be 5 times 7, 2 times 5, 2 times 5, times 3 times 11, 3 times 11, 2 times 3. We set like this. Now we reduce. We reduce like this. 2 times 7 times we reduce 2 times 11. Now we have 2 times 2, 7 times 11. We have to compute like this. In code, this is D1, N1, N1, this is D1, N2, this is D2. Then here, it becomes N1, N1, this is N1, N2, D1, D2. Here it becomes N1, D2 times N2, D1. Then we reduce like this. If we reduce, it becomes N1 prime, D1 prime times N2 prime, D2 prime, where N1 prime is this number actually, N2 prime is this number, D1 prime is this number, D2 prime is this number. Then we have result like this: D1 prime times D2 prime, N1 prime times N2 prime. So we have to compute it this way. This is multiplication. Now, addition of two rational numbers. For example, 35 over 6 plus 33 over 10. It would be 3 times 2 times 3, 5 times 7 plus 2 times 5, 3 times 11. To evaluate this, to compute this, we have to do like this: 2 times 3 times 5, 2 times 3 times 5. Then here 5 times 7 times 5 plus 3 times 11 times 3. We have to compute like this. Now let's see. This is LCM of two numbers. This is LCM. I would say LCM. Least common multiple of 6 and 10. So it is I would say LCM, and this number is N1, N2, D1, D2. This number is N1 times, let's say 5. How we get 5? 5 here. So we to get 5, we have to say like this. 2 times 3 times 5 divided by 2 times 3. It means this is L. This number is D1. Like this. So it means D1, L over D1. D1 is this number. Then it is 5. Right? About this term is N2 times 2 times 3 times 5 over 2 times 5, 2 times 5, 3. This number is L over D2. So we have to say L over D2, like this. So this is the equation for rational number addition. We have to compute like this. Now I move to my laptop computer and implement NCR or NR, the number of combinations, correctly. First I will implement GCD, Euclidean Algorithm GCD. Then I will implement the LCM with common multiple. Then I will implement rational number class. Then I will implement it correctly. I am moving to my laptop. About the Euclidean algorithm, theory and implementation, and generalize the Euclidean algorithm, please watch my 2 previous videos. I already filmed previously. Please watch them. Okay, let's get started. I created an empty solution in Visual Studio. I include IO stream. Then I include, okay, it's good enough. I will include CSDD, LIB, SDD, INT. This one. Then we are creating GCD Euclidean algorithm first. INT, GCD, INTA, INTB. I will use template. Template. Type name T. INT, GCD, T, GCD, TA, TB. Euclidean algorithm is pretty simple. R, while R equals A modulo B not 0, A equals B, B equals R, return B. About Euclidean algorithm, please watch my previous video. I made mistake here. If B greater than A, then we have to swap. Utility like this. Then at this point we have Euclidean algorithm GCD, greatest returns greatest common divisor. Now we are calculating LCD, LCM, least common multiple. Template, type name T. Here, T, LCM, TA, TB. Here, we first calculate G, GCD, A, B, then T, we can return like this. Return A over G times B. It is simple like this. Now we are creating rational number. Template, type name T. We will need type trace. I will name it unsigned, SIGNED, rational, like this. Private, T, I will say public, using, I will use using value type equals std. I need type trace, include type trace. Here, make unsigned T. Okay. Here, value type M, N, numerator, value type MD, denominator, public. I will create a reduce function, void reduce. Here at this point, I will let like this. Value type G, GCD, this M, N, this MD. You get greatest common divisor. Then this M, N equals G. This M, D, G. Like this. Now we are creating unsigned rational T. In this case, this is default. Unsigned rational T, P, T, Q M N P M D Q. Here, reduce. We will create another one, unsigned, rational, T, P, T, I would say M, D, N, D, N, D, bull. N, D. Here, M, N, M, D, D. We do not call reduce in this case. In this case, we do not call reduce. Now, we will create some more functions. We will create rational, right hand side, I will say default, copy constructor, rational operator, assignment operator, I will also say default. Two more. Also default. Here, default. Then this is destructor. It will be default. So now we are defining operator. Multiplication. Here, please remember the code I explained in my previous a few minutes ago. I would say no, I'll name it R, just R, rational number R. This would be M, P, R, M, P, here, MP times R, MP. MQ, no, This is mn, md, mn, rmd. This should be md times rmd times md, like this. Here, rational r1 this mn r m d, unsigned rational r2 this should be RMP MD. So now we computed M and would be R1 MP times R2 this MD R1 MD times R2 MD. We did multiplication. Now we are doing addition. Please remember this. Here LCM over MN times LCM over A plus N times LCM over B. So it can be, we have to get LCM first. T, L, I would say L, LCM, MD, R, MD. Now return. Oh, we should return here. I think we may return. No, I would set it void. This MN should be MN times LCM L over not this D1
not D1, MD. Here it should be RMD. Yeah. MD. Sorry. We have to make changes here. T M equals M this M and D equals this M D. We have to save it for later use. Here N D. This is N. Okay. It should be N times L over D plus R M N times L over R M D. This MD equals L. Now we reduce. Okay, we made addition now. Now we define operator. Apply AND, STD, O stream operator, STD, O stream, OS, constant, unsigned, rational, R, if R MQ no MD equals value type sorry, I made a mistake here. Template type name T signed T value type one R M N else OS R M N R M D. Okay, now we test. int main. We first test the GCD, SCD, cout, GCD, 2 times 3, 2 times 5. We have value 2 here. We are testing GCD, SCD. and there. Now let's run. No, we will test std, cout LCM as well. GC LCM 2 times 3, 2 times 5. This value should be 30. Okay, so let's run. We have to like this. Okay, 230. We understand GCD, greatest common divisor, and least common multiple works correctly. Okay. Now we are testing rational number, unsigned, rational, int. Let's say R1, 2 times 3 over 2 times 5. Now let's see if this rational is displayed properly. std cout R1 std, and there it should be displayed as 3 over 5. Sorry, we have to do return OS like this. Okay, 5 over 3. Okay, 5 over 3. Now we are doing multiplication. We say 2 over 3. R2 would be 3 over 2. R3 no, R1 should be R2. We should have R1 should have number 1. std cout R1. It should be mn. Okay, let's try it. Okay, number 1. Let's try something else. 5 times 7. 2 times 3. 3 times 11. 2 times 5. Okay. The result should be let's test. Let's see first. Okay. I think the result is correct. Let's do some calculation. So it basically means we are doing calculation like this. Sorry. We are doing calculation like this. Here, 5 times 7 over 3, 2 times 3 times 3 times 11 over 2 times 5. So the result, this cancels out, this part cancels out, and this part cancels out. So for this would be 2 times 2 over 7 times 11. So the result is correct. See, the result is correct. Now addition. If we want to do some addition, we can do like this. Wow. I'm not sure if it is correct or not, but I will not check it. I will not use it for the time being. If this value is wrong, please correct it. Or we can check it here once again. Addition. We got, no, we made a mistake here. Not this. It should be M D R M D. We made a mistake here. And here. D. Yeah, D is MD. So M. I think this is correct. Sorry, it should be MN. No, it's correct. So if it's wrong, please check once again. I'm going to move combination. Okay, here. Template. Type name T COMB combi T N T R. First, if R greater than N, then we return 0. This is error case. Okay, so this is error case. Else if R equals 0, let me check. R equals 0 or N equals R, then return 1. Else if R equals N minus 1 or R equals 1, return N. Else here, if R greater than N minus R, then we let R be N minus R. Yeah, unsigned rational. We will create 2 1. This is the, no, we will use the correct one. Unsigned rational. I would say RLT. It should be T RLT, and by default it is 1. Well, I can say by default, I can say it like this. It doesn't matter right now. Then for T I equals 1, I will do like this. n, or you can say n r. Here r equals r plus I RLT times unsigned rational n minus I r minus I. Return RLT. Now we are testing combi. We will create one more. Rational, I will say like this. Double. In this case, we will say double RLT equals 1. Instead of doing this here, like this. Here I made a mistake. I need another function. Okay, I will remove this. Okay. Then when permutation is 5, combination is 5, 0, 1, the values are working properly. When 10, all the same, 20, same, 30, see, when we start with 30, we can notice the difference. This is the correct one, this is the wrong one. You can see the difference, right? So let's try with more advanced one, with bigger ones. So for example, 40 combination 0, 41, 42, like this. This computation is correct. This one on the right hand side is using double right hand side. Here CB2 is right hand side, and CB1 is using rational number we created. See, the result is different. This result is actually correct, so this is wrong. So we cannot use this function. We cannot use this function. We cannot use this. So it gives wrong computation. So this concludes how we implement rational number. This implements rational number in this session of video. We also use the rational number properly to calculate combination. Thank you for watching.